that was being debated at the time was the idea of its being stellar nucleosynthesis. And so the idea is that the nuclei were formed in stellar interiors and then spread throughout the universe in supernovae. And in the 1950s, the way the debate went was there was one side that believed in the expanding universe that argued for primordial nucleosynthesis sort of being the source of the abundance of nuclei. And that theory did pretty well when it came to explaining this number, the ratio of helium to hydrogen, but didn't do very well when it came to heavier elements. And then at least what was known at the time. And then the other side, which was a steady state model, which wanted to argue the universe was never very hot, it's never been hotter than it is today, things have been in a steady state. Well, they had to find some way to have nucleosynthesis, and they knew a lot about, by that time, about nucleosynthesis, what happens in the cores of stars, and they knew about stellar nucleosynthesis, so they argued for stellar nucleosynthesis. And they did a good job of getting the trace elements, but they did a bad job of explaining this initial abundance. And so I mentioned earlier this set of radio debates between George Gamow and Fred Hoyle about expanding universe versus steady state universe. That's exactly what they were debating. And central to that debate was it this or this? And of course we know the answer today is it's both. Okay, so the light elements are better correctly explained here. The later processing in stars accounts for the heavier nuclei. So it's one of those situations, again, one can think about these analogous situations that are occurring today, where there are debates that occur that it's either A or B, and the answer may be more subtle. Maybe some combination of A or B, or maybe some C. Yes?
Did you mention how we know the hydrogen and helium region?
So this is done by various kinds of astronomical measurements, measuring around certain kinds of stars. And so I'll just put astro measurements. It's an art form how to extract this number, because you have to choose certain kinds of stars which you think represent abundances which are close to initial abundances, or certain stars. I'll just say certain stars. Again, a long story, long story, decades-long story.
How do we know that most of this mass is in the stars?
Pardon?
How do we know that most of the mass is in the stars?
Most of the mass isn't in the stars. The question is, where do the trace elements come from? So the trace elements. So if our understanding of the primordial nucleosynthesis story is correct, that doesn't produce nearly enough trace elements compared to what we observe. Okay? And where do we observe those trace elements? Concentrate around where there have been stars, or where there are currently stars. Okay? Which is consistent with the idea that the stellar nucleosynthesis story. So again, it's a long story how you put these two together to see if you can explain the entire periodic table. And parts of that story are still, if you've been following the news, are still emerging today. So for example, if you look at the recent LIGO incident, discovery of neutron stars colliding, one of the interesting things about neutron star collisions is they produce heavier elements in greater abundance than just ordinary stars do. So it's probably still an ongoing story to have a complete understanding of the periodic table and where all the different contributions come from. Yes.
Alex.
Yeah.
Roughly speaking, what abundances of hydrogen and helium would stars create that would falsify?
Way below, because there's a certain. It's again a story, but there's a roadblock in the way that stops them from producing a lot of helium on their own. Energy roadblock. Yes.
Grace.
Yeah.
Does the primordial nucleosynthesis, did that produce the helium also, or just the hydrogen?
Well, the hydrogen hydrogen means protons. So we're saying the universe was once hot enough that there were no nuclei heavier than individual protons. Okay, so that's what so the hydrogen's already there, if you like, in the form of protons. And there's also neutrons around. Okay, so so the question is how to get the protons and neutrons together to make nuclei. And it's a bit of a race because neutrons, neutrons which are outside the nucleus, individual neutrons, have a finite lifetime. They decay to protons and electrons and neutrinos in 10, 13 minutes or something like that. So this could not have occurred long after the first few minutes. It has to have occurred when the Earth was cool enough that they could remain bound when the protons and neutrons come together, and yet not so late that you ran out of neutrons. Otherwise, we'd live in a much less interesting universe. It's kind of interesting that it's kind of a close call. Yes.
So, sort of going back a bit when we talked about the CMB and the expansion of the universe, was it observing the CMB that had a signal with the universe expanding, or is it because I remember I think that it was initially the redshift of the galaxies that was suggested the universe expanding. So is it based on the fact?
So the steady staters were not arguing with the expansion of the universe.
Okay.
That's it. So Einstein had the idea. So static versus steady state, which sounds to the ear like they're talking about the same thing, but they're fundamentally different when we talk about that in cosmology. Static really means no expansion. Okay. Steady state had to accept Hubble's result that the universe is expanding. But then what they proposed is new matter, as the universe expands, which would normally decrease the density and change the temperature, new matter and radiation is created. Okay. In just such a way as to keep the universe in a steady state, to keep the temperature and density the same. So that means that the temperature would never have gotten hot.
Okay, and we're saying that the CMB can tell us which way.
So the first thing that CMB tells you is, when you look out in space, that there's some place beyond the galaxies which was much hotter than the stuff that is closer to us. Yeah, that's what it's telling us, which is consistent with the idea that the universe has been expanding and cooling. So that created a real problem for the steady staters.
Wait, I think I'm missing something. But how did we know it was hotter? Given that it's.
Because it has been trapped. So by now we're accepting the idea that the universe is expanding. We know it's coming from beyond the galaxies, and the universe has been expanding during the period that the universe that radiation has been traveling to us, which means the light has been redshifted.
Okay.
And it's been redshifted, it's been cooling. Then you can work your way backwards and say, okay, well, how hot was it? Oh, it was a few eV, much hotter than the average temperature in the universe today. So today, when we detect it, it's a few degrees Kelvin. When it was emitted, it was a few thousand degrees Kelvin.
So if the steady staters were right, what would we have seen?
That's it, one more time?
If the steady staters were right, what would we have seen instead?
Well, first of all, the first inclination was they never predicted there should be such a thing.
Oh.
Okay, so now they react, okay? They see the data, they say, well, maybe it's dust near us. That's what that idea that I was mentioning earlier. It could be dust cloud near us that was hot. And they have arguments why it wasn't so reasonable that it would be a few degrees Kelvin, because after all, the radiation we receive is a few degrees Kelvin, and it's nearby dust, so why not? Okay, and how do you defeat that? Well, it actually took, from the 60s to the early 90s, when we began to measure the spectrum accurately enough to just see how precise of a black body it is. And the more precisely you measure that, then the argument I gave kicks in and says, sorry, if we're really gas pooling near us, and there was this thick gas this dust cloud near us, it would have to be so thick, it would have to be so thin and so thick that it would obscure seeing the galaxies, or so broad that you would not get a single black body spectrum. So again, it's like all this bits of information. It's like a puzzle. It's not, nothing screams out to you in seeing the radiation that it must be what we interpret it to be. You have to put it together with other observations and other measurements that we make, and precision helps a lot. And nowadays you can measure some of these properties much more precisely. So if you look at the original discovery of the cosmic microwave background by Penzias and Wilson, there was supposed to be proof